good day, everybody. And once again, we're back together. All right, so we are looking at question number 3 from our technical science paper 1 from November 2024. So please, if you haven't subscribed, just make sure you're part of the family. All right, let's go right into the question. So they say to us, a gun is loaded with a bullet of mass 157 grams. Okay, already I'm seeing we might have to do a conversion there. That is mounted on a trolley at rest on a frictionless surface. The combined mass of the gun and trolley is 3.2 kilograms, and the bullet is fired at 400 meters per second due east. Right. So the first question is, state the principle of conservation of linear momentum in words. So remember, we say that in an isolated system, the total linear momentum is conserved, or you can say the total linear momentum remains the same. Right. Another way that we can state this is, in an isolated system, momentum before collision is equal to momentum after collision. All right. Now, so they say to us, calculate the velocity of the gun trolley system after the bullet was fired. Right. Now, ladies and gents, we need to be very, very aware of what scenario we have here. So initially, we had a gun and a bullet, right, that were at rest. Okay. So which means momentum before collision was actually 0. Right. So what I'm going to do is, let's try and answer the question over here. Okay, I'm going to try and draw a gun. Okay. So there's our gun. It has a bullet on the inside, right? So these are sitting on this trolley, right? But what do we know? We know that they are all stationary, right? But after collision, something must have happened to the gun and the trolley system, right, when the bullet is now moving outside. Okay, right. Now, but we were told that the bullet is now moving at a speed of 400 meters per second. Okay, we know that that's 157 grams. Okay, so we want to know what will be the velocity of the gun. Okay, let's just switch this thing off. Okay, what will be the velocity of the gun as well as the trolley system? Right, so we're going to say, well, sum of momentum before collision, okay, will be equal to the sum of their momenta after collision. And please allow me, ladies and gents, right? So I'm going to say, well, this is the mass of the gun plus the mass of the bullet. This is before collision, so the initial velocity, we know that it's going to be 0. This is mass of the gun, velocity of the gun after collision, mass of the bullet, velocity of the bullet after collision. Right, and it's very important for us to choose a positive direction, right? So I'm going to say, take the direction of the bullet, okay, to the right, or you can say to the east, as positive. Now, in this case, I'm just simply going to say, well, this is going to be 0, right? Now, the mass of the gun as well as the trolley, they said to us this is 3.2, right, multiplied by the velocity. That's what we're looking for, the velocity of the gun, right, the final velocity. Then the bullet. Now, remember I said to you, we need to convert this. So we're going to say, well, the mass of the bullet is 157 divided by 1,000. So remember, we are converting from grams to kilograms. And so this will be 0.157 kilograms. Okay, so please keep that in mind. We divide that by 1,000 because we're given the mass in grams. All right, so we go for it, ladies and gents. So this is going to be 0.157 multiplied by, that's 400 in the positive direction. Please keep that in mind. Okay, right, so let's try and calculate. So we've got 0.157. In fact, if we take it to the other side, 157 multiplied by 400. Okay, that gives us 62.8, and if we take it to the other side, it becomes negative 62.8. This is equal to 3.2 velocity of the gun. Okay, final. And we're going to divide this by 3.2. Okay, so when we divide by 3.2, I get a velocity of the gun and the trolley system to be negative 19. And please remember, it was a negative divided by positive. So I'm going to say to be negative 19.63 meters per second, right? Now, that negative simply tells us that it's going to be 19.63 meters per second to the left, or you can say to the west. Okay, right, and that is how the cookie crumbles in that case. Right, so that's what we got for the gun as well as the trolley. Right, so let's continue on to the next question. They say, what type of collision is this? Write down elastic or inelastic. So that's definitely going to be, sorry, I almost wrote the elastic. So that's going to be an inelastic collision. Remember, how do we define an inelastic collision? It's a collision that where kinetic energy is not conserved. Remember that immediately when you fire a gun, you're going to hear a sound, there's heat that is generated. So you are converting that kinetic energy into other types of energies, right? So in this case, they say explain the answer without any calculation. Okay, we will say that kinetic energy, okay, is not conserved. Okay, nothing wrong if you said that kinetic energy is converted into other forms or other types of energy, right? That is how the cookie crumbles. So let's go to the next question. They say the change in velocity of the gun trolley system is noticeably less than that of the bullet. Okay, give a brief explanation for this observation. Okay, now please remember, guys, that the change in momentum both for the gun as well as the bullet are exactly the same, right? What is different, however, right? So what is different is going to be the mass of the two, right? Now remember Newton's second law, right? In fact, let's do this. Acceleration is F net divided by the mass, okay? So what do we note? The bigger the mass, the lesser the change, in this case, of the acceleration, okay? So as a result, that is why the gun would have a lesser velocity. So we can say that the gun has a greater velocity. Not a greater velocity, rather a greater mass. The gun has a bigger mass than the bullet. Okay, than the bullet. Okay, according to Newton's laws, or we can say that the force exerted on each is constant. On each is the same, right? Only in opposite direction. That's according to Newton's third law, right? Is the same. And therefore, the gun, okay, I don't have much space to write this, so you can say that the gun will experience a lesser change in velocity. Okay, right, so it will experience a lesser change in velocity. All right, ladies and gents, I hope that you got that. Okay, as we go on to the next question, they say after the bullet is fired from the gun, okay, it strikes a stationary block of wood, okay, horizontally, and then comes to rest inside the block, as shown in the diagram. They say to us, calculate the change in momentum of the bullet. Right, so in this case, what will be our change in momentum? Okay, I'm going to just calculate it. I'm looking for a space there. Right, so our change in momentum will simply be the mass of the bullet multiplied by the change in velocity, right? So that's final velocity minus the initial velocity. So this is where we need to be very careful. Which one is our final velocity? Our final velocity is when it stops, right? So that's going to be 0.157. Final velocity is 0. Initial velocity is 400. Okay, and what do we get there? So we're going to say 0.157 multiplied by negative 400. Okay, and we get negative 62.8 kilograms meters per second. Guys, and I cannot emphasize enough how important it is for us to get the correct SI units. Okay. All right. So that is important. So it means that the change in velocity will be in the opposite direction. And that makes sense because the wall exerts a force on the bullet, okay, that causes it to slow down. Okay. So in this case, it means that it will be 62.8 kilograms meters per second, okay, to the west, or you can say to the left. Nothing wrong with that. Okay, and then finally they say calculate the time taken for the bullet to come to rest if it experienced a net force of 1,000 newtons. Right, so we are now going to use the impulse momentum question. F net multiplied by the change in time will be equal to the change in momentum, right? So in this case, we know that our net force is 1,000. We want to find out the time that it will take. And the change in momentum, we said that is negative 62.8. And all we need to do is divide there by 1,000. And there we go. So the change in time will be, okay, so we divide that by 1,000, and that gives us 0.0. In fact, we need to be very careful here because the force will also be in the opposite direction. In fact, that's why we're getting a time that is negative there. And remember, you can't get negative time, guys. So 0.063, okay, seconds. Right, and that is going to be the time that it takes for the bullet to come to rest. Ladies and gents, that would have earned you 18 marks, hey? 18 marks in total. And I think this is one of those sections that you need to make sure that you get those full marks, all right? Well, and that brings us to the end of this question. I hope that you were able to follow. From me for now, I'll see you guys again next time when we do question 4. It's sharp, sharp.